Welcome to the online course, Road Subgrade and Pavement Engineering. This course is hosted by School of Highway at Chang'an University. My name is Peng Li. From this chapter, we are going to talk about concrete pavement. In this chapter, there are three sections: Introduction, Concrete Pavement Stress Analysis, and Concrete Pavement Design. For the last design section, it needs 2 lectures to cover the entire content. In this introduction, we will learn what is a concrete pavement, types of concrete pavement, and most importantly, the concrete pavement distress and serviceability. Concrete pavement is also called rigid pavement. Its surface is constructed with Portland cement concrete. The first concrete road was built in 1893 in Bellefontaine, Ohio, in the United States, more than 100 years ago. And it is still in service today. Concrete pavement have been utilized for all types of pavement applications, including street, highway, parking facilities, industry facilities, and airfields. Concrete pavements offer a long life, low maintenance alternative for all pavement application. Previously, we already learned the analysis and design of asphalt pavement. So what are the differences between asphalt and concrete pavement? Because of concrete's high stiffness, concrete pavements tends to distribute load over a relatively wide area of subgrade. The concrete slab itself supplies a major portion of a rigid pavement structure capacity. Flexible pavement, built with less stiff materials, does not spread load as well as concrete. Therefore, concrete pavement usually require less layers and smaller thickness to spread load to the subgrade. The concrete pavements last longer and the maintenance requirement is also low, but it costs higher than asphalt pavement, and when it breaks, it will be very difficult to fix. When you drive on concrete pavement, you may hear a constant noise due to the friction between tires and grooves. That is another disadvantage of concrete pavement. Similar to an asphalt pavement, a concrete pavement is also composed of several layers, including concrete slabs, base, and subbase. Compared to asphalt pavement, one distinguishing characteristic of concrete pavement is that the pavement surface is divided into slabs. Transverse joint and longitudinal joints can be easily identified on a concrete pavement. Usually, dowel bars and tie bars are used to connect slabs along transverse joint and longitudinal joint. Surface textures and smoothness is also very important, which provide a comfortable and safe driving ground. Since that pioneer project in Ohio 100 years ago, concrete pavement have been refined into 3 primary structure types: jointed plain concrete pavement, short for JPCP, jointed reinforced concrete pavement, short for JRCP, and continuously reinforced concrete pavement, short for CRCP. JPCP is the mostly used type of concrete pavement due to its low cost. The primary item that distinguishes among these 3 types of concrete pavement is the joint system used to control crack development. JPCP utilizes joint to control where cracks develop and then rely on aggregate interlock and in many cases, dowel bar to transfer the load from one slab to the next. CRCP allows the pavement to crack more randomly, but utilize an increased amount of steel as reinforcement to ensure the cracks remain extremely tight throughout the pavement's life. GRCP is an intermediate between JPCP and CRCP. It utilizes joint and dowel bar similar to JPCP, meanwhile featuring reinforcing steel to keep cracks tight between the joint. There is another type of concrete pavement called pre-stressed concrete pavement, short for PCP. As we know, concrete is weak in tension, but strong in compression. The pre-application of a compressive stress to the concrete greatly reduces the tensile stress caused by the traffic load and thus decrease the thickness and concrete required. The PCP has less probability of cracking and fewer transverse joint and therefore result in less maintenance and longer pavement life. But it is the most expensive one. Now let's move to pavement distress and serviceability. When we design a pavement, we design it to resist to distress and make the structure to last longer. Pavement serviceability is the capability to resist distresses caused by traffic load, environmental effects, and to meet service requirements. So one of the most important resistance to load-induced stress. Because of concrete's high stiffness, concrete pavement tends to distribute the load over a relatively wide area of subgrade. The concrete slab itself supplies a major portion of a rigid pavement structure capacity. By increasing the thickness of pavement, layers and material strength, we could increase the overall strength of pavement and therefore increase the resistance to the load-induced stress. Pavement distress caused by the load-induced stress includes, but not limited to, transverse cracking, longitudinal cracking, and corner cracking. And usually, they are the result of combined load stress and thermal stress. Resistance to thermal stress. Thermal effect cause curling stress and compressive or tensile stress. Let's look at curling stress first. On the left-hand side, the figure illustrates the development of curling stress during the day and at night. Be careful. You may easily make mistakes on the direction of the forces. During the day, when the temperature on the top of slab is greater than that at the bottom, the top tends to expand with respect to the natural axis, while the bottom tends to contract. However, the weight of slab restrains it from expansion and contraction. Thus, compressive stress are induced at top, tensile stress at the bottom. Combined with the load-induced stress, this becomes the worst scenario, and it also the condition we need to think about during the pavement design. At night, when the temperature on the top of slab is lower than that at bottom, the top tends to contract with respect to the bottom. Thus, tensile stress are induced at the top and compressive stress at the bottom. On the other hand, thermal effect also induce compressive or tensile stress to entire slab due to uniform temperature variations from time to time. This will affect the design of joint spacing. The associated pavement distress with thermal effects including transverse cracking and blow-up. There are other types of concrete pavement distress, including faulting, spalling, surface lamination, materials-related crack, and surface defects. Usually, spalling happens at the transverse and longitudinal joint or cracks. Spalling in concrete pavement is one of the most common concrete pavement distress. The spalling may develop predominantly in the top few inches of slab or may develop at great depths below the surface. Depending on the environmental conditions, eventually reaching full pavement depth. Faulting is the difference in elevation across a joint or crack in a pavement due to loss of load transfer. It is a symptom of the loss of ununiform base or subgrade support, normally from the lack of dowel bars. And that's all for today. Thank you.